So I want to look at some additional reactions of your carbonyl compounds. The first reaction that we're going to look at is the reaction of an acid chloride with a Gilman reagent. In this reaction, we're going to be replacing the chloride of our acid chloride with the alkyl group from our Gilman reagent. So that in this case, the product of our reaction looks like this. Where we've gone from an acid chloride to a ketone. So that the methyl group from our Grignard reagent is the methyl group that's now on this ketone. This reaction works specifically for acid chlorides, where in this reaction our Gilman reagents are not quite as strong of a nucleophile as our Grignard reagents, so the behavior in this type of reaction is different and we get the ketone as the product of this reaction. We can also have ketones and aldehydes undergo a reaction with acetylide ions. And if you remember back to first semester, acetylide ions are when we have a deprotonated terminal alkyne, and our acetylide ions are capable of acting as a strong nucleophile. So in the reactions with ketones or aldehydes, an acetylide ion is going to react just like a Grignard reagent would. And in the reaction with this ketone, the product that we would get out of this reaction is this one. Where my acetylide ion forms a carbon-carbon bond with the carbonyl of my original ketone. So that this carbon right there is this carbon right there in my product. As I make an acetylide ion as a strong nucleophile, again, that comes from the deprotonation of a terminal alkyne. So I can take a terminal alkyne like this one, and I could treat it with sodium hydride or sodium amide, NaH, or NaNH2. Those are the two strong bases that we talked about last semester to do this reaction. And I get that deprotonation and get my acetylide ion, which will behave as a strong nucleophile in a reaction like this one. There's lots of alkyne chemistry that you could then go on to do with a product like the one that you see here. In number 3, we're going to be looking at what's called chemoselective reductions. And the term chemoselective means that one functional group will react selectively over another. So the principles that we're going to be using when we run these chemoselective reductions are either control of our stoichiometry or taking advantage of an increased reactivity of one functional group over another in our molecule. So then in the first case, case A, I have an aldehyde and an ester in this compound. Here's my aldehyde functional group, here's my ester functional group. I'm going to be treating this compound with sodium borohydride followed by an acid workup. And there's a couple things I want to remember as I think about this reaction. One of the first things that I want to remember is that sodium borohydride was one of my weak reducing agents. That means that it only reacted with the most reactive of my carbonyls. When it comes to my carbonyls, I have an aldehyde and I have an ester. And I know that my aldehydes are more reactive than my esters. And when I think back to the reductions of aldehydes and esters, I know that sodium borohydride reacted with an aldehyde and did not react with the ester. So it's a weak reducing agent and it does not react with the ester. So that in this reaction, no matter how much sodium borohydride I put into this reaction, it only has the capability of reacting with this aldehyde, never with the ester. So based on that, predict the product that you would get out of this reaction. So that would be the product that you get out of this reaction, where it is my aldehyde carbon that reacts And my ester carbon remains completely intact in this reaction, again, no matter how much sodium borohydride I add. In the second reaction, in part B, we're looking at a compound that contains both an aldehyde and a ketone. Our reducing agent in this reaction is also sodium borohydride, but here we have control over the stoichiometry by adding just 1/4 of an equivalent. Because each molecule of sodium borohydride has 4 equivalents of H- that it can use in the reactions, this 1/4 equivalent of my reagent is going to be equivalent to 1 equivalent of H-. That means that either my aldehyde or my ketone will react under the conditions of this reaction because I've controlled the stoichiometry of my reagent. So that when I treat this with 1/4 of equivalent of sodium borohydride, only my more reactive functional group will react in this case. That's going to be my aldehyde, and so the product that I get out of the reaction is this one. Where it is my aldehyde carbon that reacted and my ketone carbon remains completely intact. So what do you think would happen in the following reaction? If I have this same molecule that contains both an aldehyde and a ketone functional group, and in this case I treated it with an excess of sodium borohydride followed by my acid workup, what would be the product of that reaction? Take a moment and predict the product. The product that we would get out of this reaction is one where both the aldehyde and the ketone are reduced to the alcohol if there's enough reducing agent present in the reaction. In the previous example that we looked at, we controlled the stoichiometry of our sodium borohydride reagent. That means that because my aldehyde is more reactive, that first equivalent of sodium borohydride simply reacted with the aldehyde. There wasn't enough sodium borohydride to then go on and react with the ketone. In the second example that we see here, there's now an excess of that reagent. So that means that everything in the reaction that can react with sodium borohydride would react with sodium borohydride. So the next reaction is a specific set of conditions that will allow me to do a selective reduction of a ketone over an aldehyde. And that's called the Loesch reduction. So here I have a molecule that contains both an aldehyde and a ketone, and I'm going to treat this molecule with a particular set of reagents. So I'm going to treat it with sodium borohydride, where I keep careful stoichiometric control of the reagent, followed by cerium chloride, which is a Lewis acid catalyst, at a temperature of -15 degrees. So my conditions that I'm using in this reaction are going to give me stoichiometric control They're going to use a Lewis acid catalyst. And I'm also going to utilize low temperature in order to help give me additional control in this reaction. The second step, as with any reduction, is an acid workup. So that in this reaction, what's going to happen is that I have a resonance structure that I can draw where for both my aldehyde and the ketone, I can look at the electrons being pulled up to that oxygen. So for both of these structures, I have significant electron density at the oxygen. And that structure looks like this. So that in this reaction, I also have my cerium 3 chloride, which will act as my Lewis acid, and it's going to be a very good acceptor of electron density, and it's going to accept electron density from the oxygen that has greater electron density. When I look at my aldehyde and my ketone in this example, what I know is that the carbon of this ketone is more stable with that positive character because it has two alkyl groups there to help stabilize that positive charge. In the case of the aldehyde, we only have one alkyl group present there to help stabilize that positive charge. So that means that this separation of charge is going to be less prominent for the aldehyde, and we're going to have a little bit more electron density at the oxygen of the ketone and a little bit more positive character at the carbon of the ketone due to the increased instability that we have from those two alkyl groups for the ketone. That means that if one of these oxygens has greater electron density to give to the cerium, it's going to be the oxygen of the ketone. That oxygen of the ketone has greater electron density. That means that it's going to donate electron density towards that cerium, and it's going to give me a complex that now looks like this. It's going to give me a complex that now looks like this, where I've taken away that negative charge at the oxygen and I've given its electrons to the cerium. That aldehyde can also go back to having that carbonyl bond intact. So that what happens with this particular structure, because I've given the oxygen's electron density toward the cerium, that's going to put an even greater positive character at that carbon. So that in this reaction, the more reactive carbon now becomes that carbon of the ketone due to the formation of that complex with the cerium chloride. So now this carbon is now more reactive, and this will be where my reduction takes place. So now my boryl hydride ion is going to send one of the hydrides to that more reactive carbon, which is now the carbon of the original ketone. And after my acid workup, where I've been able to selectively reduce the ketone over the aldehyde using my Lewis acid catalyst, stoichiometric control of my reagent, and low temperatures. I can do a hydrogenation of an aldehyde or a ketone to an alcohol using hydrogen gas and a particularly reactive catalyst called Raney nickel. So if I have this aldehyde and I treat it with Raney nickel and hydrogen gas, the product that I make out of that reaction is this alcohol. And if I take my ketone and treat it with hydrogen gas and Raney nickel, the product that I make out of that reaction is this alcohol. Where this carbon of my aldehyde is this carbon of my product, this carbon of my ketone is this carbon of my product, and I've essentially added a molecule of H2 across this pi bond. This carbon of my carbonyl gets a bond to a hydrogen. The oxygen of the carbonyl also gets a bond to a hydrogen. As we look at this example, recall that we had a special reaction that took place if we had a benzylic ketone, like this molecule here. We had this ketone, and we treated this ketone with hydrogen gas and palladium on carbon. What would the product of that reaction be? The product of that reaction is this one here, where that benzylic ketone in the presence of hydrogen gas and palladium on carbon gets reduced to the CH2 group at that benzylic position. Notice that my ketone that's not in the benzylic position remains unaffected by this reaction. Raney nickel is a more reactive hydrogenation catalyst than palladium on carbon.